Dear students, welcome back. This is Dr. Biju Vasudevan. In this video, we are going to discuss methods of applied mathematics 3, Math 315 for week number 4. Week number 4 for regular semester stream. So you should compare week 3 and 4 together for your week 2 of summer semester. For transforms of, so this video starts with transforms of periodic function. And then we will go to Dirac delta function, and we end with the system of linear differential equations. Okay. Here we go. Transform of a periodic function. So first the question is, what is a periodic function? See, have you noticed in sine and cosine? With this one, 0, pi and 2 pi. Up and down is over here, isn't it? And again it starts repeating the same pattern. It's going on for every 2 pi. So such a function, the function that repeats its behavior after some period, is called a periodic function. So here the function sine x is a periodic function with the period 2 pi. Period 2 pi. So to sine is also another example of a periodic function with the period t is equal to 2 pi. If I give sine nx, then you can find the period as 2 pi over n. 2 pi over n is the period of sine nx. Similarly for cosine nx. But tan x is the periodic function with the period pi at 2 pi. Right? So they are naturally periodic functions. So let's read the definition now. If a periodic function f has period t, t is non-negative, positive, then f of t plus capital T is equal to f of t. After the period time t, it will be behaving the same f of t, right? The Laplace transform of such functions. If a function is known as periodic function, we don't need to integrate it from 0 to infinity. We integrate it from 0 to t, the period t, e raised to minus st, f of t dt, everything is same in the formula of basic Laplace transform, but it's not for 0 to infinity. Initially we write capital T here, and then write this term in front of it, 1 over 1 minus e raised to s times the period t. Period s should be known. So that is the formula. The function is piecewise continuous in the interval, and the exponential order, everything is true. Whatever the essential necessary conditions, sufficient conditions for the existence of Laplace transform should be true for this function f of t. And we don't need to verify them. We just apply. If we know that the function is periodic function with the period t is known, then we use this formula, right? That's what we are going to do in this chapter. So remember this formula, the same fundamental formula of Laplace transform, but instead of 0 to infinity, we write 0 to capital T. But there is a constant of 1 over 1 minus e raised to minus st. So this term is independent of small t. There is no small t. So integration will not disturb this one. Fine. Let's go to the first example. Here, the periodic function has been graphically defined. We know, some functions are not naturally periodic functions. For example, f of x is equal to x is not periodic. But when we restrict the period, when I write f of x plus t is equal to f of x, and I define this one from within 0 to 1. So from 0 to 1, this is x1, so 0 to 1, f of x is x, and this statement says that this is periodic. It starts up again from here. After 1 unit, it will start from this one. So though the function is not naturally periodic, we can convert them into periodic function by restricting the period interval and then writing this statement, right? It becomes periodic. So this way we can define periodic function, or otherwise by graphically. If I give the graph, it gives you the periodic function. Now let's check the formula of this function. What is it? F of x, f of t, you can write whatever in x. It's positive 1 and negative 1. Positive 1 in the interval 0 to a. 0 less than t less than a. And negative 1, positive 1 in the interval and negative 1 in the interval. This is equal to, okay, you can make equality anywhere, a less than or equal to t less than or equal to 2a, isn't it? Okay, equality does not play a big role here, so that's it. This is the equation of this function. Now we have to apply the formula for Laplace transform of the periodic function. What is it? A Laplace transform of a periodic function. So here, by using the graph, we understand this periodic function. So we don't need to write f of t plus capital T is f of t. We don't need this one. Right? Now formula says 1 over 1 minus e raised to minus s times period. What is period here? The total period. See, this is the period 1. From a 0 to 2a it behaves same. After that it repeats the same point. So the period is 2a, 0 to 2a. T is 2a, so e raised to minus s times 2a in the outside, and integral 0 to 2a e raised to minus st f of t dt, and 2a can be separated into two parts, 0 to a and 0 to a and 2a to 2a. This is what we are going to do here. So now, as per the formula, it is 1 over 1 minus e raised to minus 2as, and the integral 0 to 2a can be separated into 0 to a e raised to minus st. In this interval the function is 1, positive 1 dt, plus a to 2a e raised to minus st negative 1 dt. Now integrate these two times, modify with the outside constant, that's it. So you will write 1 over 1 minus e raised to negative 2as, and the first integration will be e raised to minus st over minus s from 0 to a, minus second integration is e raised to minus st over minus s from 0 to 2a, a to 2a. Now further simplification, outside element will be remaining same. Now substitute upper and lower limit, simplify, that's it, right? So when we substitute upper, this negative s I think can be commonly taken outside, and a will be replacing t e raised to minus sa, and then 0 will be replacing t e raised to minus 0 is 1. Same can be done for the second term. Let's do it here. That is 1 over 1 minus e raised to minus 2as, 1 over negative s has been taken, upper limit t will be replaced by a e raised to minus as, and upper limit is 0, for lower limit is 0, that is e raised to 0 is 1. This is for the first term. For the second term, e raised to minus 2as minus e raised to minus as. Now the close bracket, isn't it? Further simplify this one, 1 over 1 minus e raised to minus 2as, the numerator this is e raised to minus as, e raised to minus as is positive, isn't it? So 2 times e raised to minus as minus 1 minus e raised to minus 2as divided by minus s. So when you change the sign, this negative can be removed. So 1 over 1 minus e raised to minus 2as, you can write this one first, positive e raised to minus 2as, because this minus will be multiplied inside for every time in numerator. So this will be positive, this will be positive, this will be negative. Minus 2 e power minus as plus 1 and divided by s. And now see this one, e raised to you can write e raised to minus as minus 1 whole square. Expand it, you will get e raised to minus 2as minus 2 e raised to minus as plus 1, isn't it? So this is the numerator here. So the numerator can be simplified as d raised to minus as minus 1 whole square divided by s, and the outside we found 1 over 1 minus e raised to minus 2as. The next step what we have to do is, this is 1 e minus as e to the power minus as minus 1 whole square. This term further simplified as, see, 1 minus e raised to minus as whole square, 1 square. So this can be 1 plus e raised to minus as into 1 minus e raised to minus as. This term can be expanded like this way. And 1 minus this square term you can separate. So what's the next step? Is this I am writing, instead of e raised to minus as minus 1 whole square, since square is there, I change this term into 1 minus e power minus as whole square. The denominator will get s times 1 plus e power minus as and 1 minus e power minus as. 1 minus e power minus as of degree 2 the numerator, degree 1 the denominator, 1 of them can be cancelled. So finally you will get 1 minus e raised to minus as divided by s times 1 plus e raised to minus as. That's the end of the problem. That's a given here, right? There are two more problems we will discuss, both of them. The triangular wave problem. Remember this one, and then we will solve it on a separate sheet. First we should identify the function. You should remember this is 0 0, this is 1 1. So this line is nothing but f of x is equal to x, and this line you should have found it will be extending to 2. This is nothing but x plus y equal to 2. Y is equal to 2 minus x. So you can write f of t is equal to 2 minus t. Otherwise there is another way to find the second equation, second line, this line. See, this point is 1 comma 1. We call x0, y0 is 1 1. And this point is 2 comma 0. We call x1, y1. So the equation of the straight line is y is equal to mx plus c, where the slope is y1 minus y0 divided by x1 minus x0. Use the elements in this one, you will get m is negative 1, and substitute in this equation, you will get y is equal to negative x plus c, and give some values for x and y, you will get c. Give x is 2, y is 0, so c is 2. Therefore the equation of the straight line is y is equal to 2 minus x, minus 2 plus minus x plus 2, isn't it? So y is equal to minus 2 plus x, otherwise x minus 2. So this line, the red line, is x y is equal to x minus 2. The black line here, it is y is equal to x. So how can we write finally this function, periodic function? Period is to see after reaching 2, again it repeats the track. See, for every 2 units it is becoming a triangle again. So the equation of the function we are writing here, f of t is t and 2 minus t. Instead of x, I am using t now. Between 0 and 1 it is t. From 1 to 2 it is 2 minus t. This is the function. Once you identify the function, the integration is quite easy. Now let's solve this problem on a separate sheet. So the function is f of t, which is t and 2 minus t, 0 less than t less than 1, 1 less than t less than t, isn't it? Okay. Now for the Laplace transform of a periodic function. This is periodic. By the graph we understand. Laplace transform of periodic function is 1 over 1 minus e raised to minus 2 minus s t. What is the period for this problem? Period t is 2 units. So that will be replaced. 0 to t e raised to minus s t f of t dt. So 1 over 1 minus e raised to minus 2s, s is t is 2. Integral 0 to 2 e power minus s t f of t dt. And this integral 0 to 2 will be separated into 0 to 1 and 1 to 2. So 1 over 1 minus e raised to 2s integral 0 to 1 e power minus s t f of t will be t minus dt minus integral 1 to 2 e raised to minus s t 2 minus t dt. Okay, now we do first integration separately, second integration separately, and then multiply with the outside constant term, right? That's it. Integration 1. What is it? Integral 0 to 1 t time e raised to minus st dt. Go back. This is the integration 1, isn't it? T times e raised to minus st dt. U is t and dv is equal to e raised to minus st. So u prime is 1, u double prime is 0. v1, so this is v is 1, v1 is e raised to minus st divided by minus s, and v2 is e raised to minus st over s square. And the formula for integral u dv, uv dx or dt, right? Is uv1 minus u dash v2 plus u double dash v3. So we don't want v3 because u double dash is 0. Only first two terms. U is t v1 is e raised to minus st divided by minus s, minus u dash is 1, v2 is e raised to minus st over s square, and now the limit is 0 to 1. So what do you get when you substitute upper limit to 1 and lower limit to 0? Upper limit to 1 where t 1 times e raised to minus s over minus s minus e raised to minus s over s square. Upper limit is done. Minus lower limit. When t is 0, first time will be 0 minus again t is 0, 1 over s square. So first integration 1, I1 we can call it. I1 will be first term you can write see both the terms have common. So first we will write it e raised to minus s over minus e raised to minus s over s square plus 1 over s square. So take s square as LCM, so multiply s and s here, right? It will be minus s into e power minus s minus e power minus s plus 1 over s square. This is first integration. In the similar way, you take a partial integration by parts and do this integration. Here u is t 2 minus t, v is this one. Or you can use general integration by parts as well, no issue. The answer for, I'm writing the answer for the second integration. Integration 1, what we have done here is minus s into e power minus s minus e power minus s plus 1 over s square. In integration 2, the second part, when you do it, you will end up with a e raised to minus 2s plus s into e power minus s minus e power minus s over s square. Now the final Laplace transform of f of t goes ahead with the outer term 1 minus e power minus 2s open the interval, open the bracket, first integration. Both have same denominator, so commonly you write s square. Numerator first term will be minus s into e power minus s minus e power minus s plus 1. Second integration result, e raised to minus 2s plus s into e power minus s minus e power minus s. See, the first term and this fourth term can be cancelled. The rest will be 1 over 1 minus e power minus 2s. This term positive, e raised to minus 2s. Next, minus 2 times. See, this term and this term got cancelled, so only 4 terms are there. This is same, these two are same, negative. Minus 2 e raised to minus s plus 1 divided by s square. The simplification should be done just like the previous problem. This numerator will become e raised to minus s minus 1 whole square divided by s square into 1 minus e raised to minus 2s. Now the next step, we will write Laplace of f of t. You will write 1 minus e power minus s whole square divided by a square into 1 minus 1 is 1 square e minus e power minus s whole square, to get the form a square minus b square. The numerator 1 minus e raised to minus s whole square can be written as 1 minus e power minus